It's good to be here. Thank you all for coming. So my topic is bootstrapping analog of the one-way MANOVA test. So let me start with the very basics, okay? So for example, let's just say we are trying to test this hypothesis, mu1 equal to mu2 versus h1, mu1 not equal to mu2. These are not vectors, just simple mu's. What test do we use? I'm sure you have taken a statistics course, right? So we basically use the two sample t-test, right? Now, this is only for the two groups. What if we have more than two groups? Then mu1 equals mu2 up to mu p, p populations. Then we do the one-way ANOVA test, right? What if these are not just numbers, but if they are vectors? Right? So if you're testing against a vector of means versus a vector of mean, then the simple two sample test doesn't work. Then we're going to have to do the Hoteling's t-square test. So in the introduction, I'm giving you the introduction for the Hoteling's two sample t-square test, and also the one-way MANOVA test is the multivariate analog of the one-way ANOVA test. So in the beginning, I'm just going to introduce those two. And then, right here, I will introduce the new test, addressing the drawbacks of the previous mentioned test. Alright? So let's go ahead and start. So again, this is the hypothesis that we are interested in. These are not just numbers, these mu's are vectors. Alright? So right here we have the Hoteling's t-square test. To do that, we need to assume these TIs satisfy this central limit type theorem. Once it satisfies that, we can use the large sample theory. I'm not going to go through all the proofs here, but we can come up with a test statistic to test the above-mentioned hypothesis. First, it will come to a chi-square distribution, but with a small sample correction factor right here. We can come to a distribution and we can test the interested hypothesis. Right? Now that's the two sample Hoteling's t-square test. And this is about the one-way MANOVA test. Now we not only have two groups, but we have p groups, p populations, and again these are vector of means. Now you might be probably wondering, so inside these I have let's say m measurements, okay? Why can't we do m many ANOVA tests, right? You could do that, but if you do that, it wouldn't take the correlations between these variables into account if you just conduct m many ANOVA tests. Okay? So that's why we need the one-way MANOVA test instead of just m one-way MANOVA test. Alright, now how do we do this test? Right here, so I'm just introducing the treatment, residual, and total sum of square matrices. Once you have those matrices, these are the most commonly used test statistics. Okay, the Hoteling's t-square, Hoteling's stress test statistics, that's very widely used. And of course, if you want to test this, we need to have distributions. Okay, at least asymptotic distributions. All of these are going to a chi-square distribution asymptotically. Then we can do the testing using that distribution. Now that is what's happening in the classical world. All right. So we can use these test statistics to test the above-mentioned two hypotheses. These two. Okay. Now, our test, well, one of our tests is a large sample test, but most of our tests are bootstrap tests. All right. So before I introduce our test, I want to introduce the bootstrapping. Okay, it's going to be a very tiny introduction, but let me go through that real quick. Okay. Now, what is bootstrapping? Okay, now let's think of this as my population. This is my population. If this is my population, what do? We usually take a sample out of it, right? Because it's usually hard or impossible to access all the data points in the population, instead we take a sample out. If you can take many samples out of it, great. But it's again impossible or hard to do. Once we have our sample, so this is my sample. We're going to treat my, let's say size n, okay? Size n. Once you have this sample of size n, what do? you consider this sample as your population and you resample out of this sample maybe B times. B is usually 1000 because it's not very hard to do, you just use your computer to do it. Okay? One main thing to mention, you have to do that with replacement. Okay? So you resample out of the sample with replacement B times. Once you do that, you will have B many samples, then you can do whatever you would like with those samples. Okay? Maybe you can find the statistics that you were interested in those samples, and then maybe find the distribution. Okay? Now, here we have a very small example. Here's my data set right here, 1 through 10. The statistics that I was interested in is the sample median. Okay? Now, what I have done? First, I did the bootstrapping, and I resampled from that sample with replacement, and I came up with a median, which is 6.5. Right? What is the median for the real data set? The actual data set, that's 5.5. But here's for 6.5. That is just how it works. Okay? Now here, the second bootstrap sample, maybe I got lucky or maybe I cheated. That is 5.5. Okay? Now this is only 2 samples. Usually we do 1,000 of those. Okay? Now that's how we do bootstrapping. Okay? Now let me go ahead and go to the Theorem methods. Okay. All I wanted to do is introduce how to do a bootstrap, a hypothesis test. But before that, let me introduce some notations. Oops. All right. So here are some notations. Okay. Now, sample mean, right? Pretty simple. Actually, it's not just sample mean, but the mean vector. Okay. So here we have a mean vector, and that's the sample covariance matrix. And here I have the I² sample homologous distances. Okay, now this is a scalar, so you can get a sense of the distances for the data points you have. Okay, now using all that, here I have a set. Actually, this is the hyperellipsoid. So this is all the distances I have, and then you cut that at another place. So most of the time it's a percentile. When you cut that, that becomes a hyperellipsoid. Okay, that's all I wanted to show you there. But this C, that's your choice. Okay, now let's take a look at this. Once you choose that C to be UN, where UN is the 100 qnth percentile of those DIs, this hyperellipsoid becomes a 101 minus delta percent non-parametric prediction region for a future value. Okay, when you choose Qn to be like this. Okay, one thing to notice, the classical prediction region has a chi-square cutoff, where ours has a percentile. Right? Now, probably you are wondering, I'm trying to do a hypothesis testing, right? But right now I'm talking about a prediction region, right? But what if we have a confidence region instead of a prediction region? Then can we do that? Can we do our test? Yes, we can, right? So that's what's going to happen. So here is where the magic happens. Okay? Now, let's take a look at this. Now, I have 2 regions right here. What is the difference between RC and RP? These both are hyperellipsoids. The only difference is the center, right? So this is centered at a test statistic, a non-test statistic. Mu is unknown. In that case, this becomes a confidence region for our mu. Now, if you place the same hyperellipsoid at a non-mu, it becomes a prediction region for a future value. Okay? Now, let me try to explain what's going on here. Maybe I should go here. Oops. All right. Now, let's just, for example, think we have T1, T2 up to TB, and IID. These are IID. Don't get confused with B. I'm just using B. Those are not bootstrap samples, but IID data from your population. All right. Once you have those, and assume mu is known, then we could use T minus mu transpose ST inverse T1, isn't it? Let's then equal to T UN, where this DUN is a percentile of those distances. Alright? We could use this as a 101 minus delta percent prediction region for a future value. Okay? Let's just say this is just 95 for the convenience. Okay? Once we have that, is that okay to go there? Maybe I'll stick around here. Okay, let's see. So what does that mean? That means this prediction region will cover 95% of those TIs, right? So let me try to draw a picture. So this is your hyperellipsoid, and it is covering some of this outside. It is covering 95% of your TIs, right? Now, what is the center? Center is our known mu, right? Now, what I'm going to do, instead of keeping that hyperellipsoid, I'm going to take that hyperellipsoid and place it on a different TI. So center is going to be different, not mu, but something else. So let's say this one, right? If I move that, this hyperellipsoid will keep the shape and the same size, same volume, and it's going to look like that, right? Just take my word for it, these two are the same size and the shape, okay? Now, if you do that, if you center your hyperellipsoid at a non-statistic, what's happening? Would that include our mu in there? If I place it here, it will include my mu, right? But if I place my the hyperellipsoid at here, what would happen? Would it consist of our mu? No. How many times it would not consist of our mu? How many times you think? 5% of the time, because this is a 95% confidence prediction region, right? Now what's happening? If you think about that hyperellipsoid, you're placing it at a non-test statistic, and it consists of our mu 95% of the time. What does that tell us? That prediction region now is a confidence region, right? So that's how you convert a prediction region into that's how you convert a prediction region into a confidence region, right? Now using those hyperellipsoid, we have our confidence region. Now we can do our testing. Okay. Now let's go ahead and take a look. Now this is how you do your testing. Okay. The first half. Oh well, I forgot one thing. This T1 up to TB, those are IID, but we don't have IIDs, right? We don't have IID data. So instead, what we do, we take the bootstrap samples, right? So everything will become bootstrap data. Okay. There are a lot of lines between coming from IID to bootstrapping, which I'm not going to explain today, but that's how we're going to do it. Okay. Instead of IID, we are taking bootstrap data. Now, once you have the bootstrap data and you come up with your prediction region, and then you convert that to a confidence region, once you do all that, you can test this hypothesis. Okay. But for now, let's just forget about two samples. Let's just say we are testing mu versus a constant, or maybe a constant vector. Okay. Now, instead of that, we're going to do mu minus c equal to 0. And then what we're going to do, we're going to take our wi's to be mu I hat star minus c. What is mu I hat? Mu I hat is a consistent estimator for our mu. Star because they're coming from bootstrap samples. Okay. And then, like I said, we have B bootstrap samples. Once you have all that, you make the prediction region describe for both and check if 0 is inside that prediction region. If 0 is inside the prediction region, we fail to reject our H0. If, reject H0 otherwise. Okay. Now that's how you do the bootstrap hypothesis test. Okay. All right. Now we can go into our new test. Okay. Right now, I want to explain why we are using this new test, and I'm going to address the bootstrapping analogs of the Botanics t-square test, which is the two-sample case, right? And then I'm going to show you some simulation and a real data example for that. And for the MANOVA test, I'm going to do the same sort of things. Okay, I haven't listed it there, but I'm going to do it. All right. Okay. I have haven't still mentioned why we are doing this new test. We already have pretty good tests out there, right? But if you look at the two-sample Hoteling's t-squared test, it is robust to these assumptions. It doesn't need the populations to be multivariate normally distributed. And the population covariance matrices doesn't have to be the same. But that test is very poor when there are outliers. Okay? I'm sure you know what the outliers are, right? Outliers are just the data point that lies far away from the bulk of the data. Okay? Sometimes they are good, sometimes they are bad. Okay? Anyway, the classical one-way MANOVA test, though, it uses a very strong assumption. It assumes the covariance matrices among the populations are the same. Okay? And also, it's a large sample test, of course, it's not robust to outliers. Alright. So we can address those issues and we came up with new tests. Okay? So first of all, let's take a look at these tests. These are the bootstrapping analog of the Hoteling's t-squared test. Alright? So here, this is the hypothesis, again, those are vectors. Now here we came up with 4 tests. Okay? What I like about these tests, if you don't like this test, you can always change them. Okay? Here I'm using the coordinate median, sample mean, 25% mean, and the RMB location estimator as the estimators. But if you don't like them, fine, you can go ahead and change to another estimator. Okay, then you have another test. Alright? But how do we conduct these tests? Right? So let's take a look at those. So here we have the test 1. Okay, so how do we do it? So that's the definition of the coordinate median. Those are just the median vectors. And you're going to make a bootstrap samples of Wj's. What is Wj? I'm taking the difference between the coordinate median for those two groups. Okay? And j equal 1 through b, that means b bootstrap samples. Okay? And then we're going to make a prediction region for those Wj's, and we're going to check if 0 is inside that prediction region. Okay? Now, if the 0 is inside the prediction region, we fail to reject our H0, reject H0 otherwise. Okay? And test 2 and 3 are very similar. All you have to do is replace this Wj by the difference between the means for those two groups, or the difference between the 25% training mean for those two groups. Okay? But I separated the test with the RMB estimator, so let's take a look at that. Again, it's very similar actually. All you have to do is take the difference between the location estimator of the RMB estimator, okay, which is known to be robust to outliers. It actually has both the location and the dispersion estimator, but I'm just using the location estimator here. And you do the same sort of thing, okay, and then you end up with your result. Okay. Now, to show our test works very well, we came up with a simulation. Okay, so now this simulation, here's the simulation setup. Okay, all the time our simulation uses 5,000 runs. Remember, we need our bootstrap samples, right? So we are using 1,000 bootstrap samples. Okay, now we wanted to see if these tests are robust to the assumption of multivariate normality. So we are using different distributions. Okay? Multivariate normal, multivariate t mixture, and a log normal distribution. Okay, and we are changing the covariance sometimes. You will see when you see the results, right? Now, we wanted our test to be outlier resistant, robust to outliers. So at a point of our simulation, we contaminated our data. Okay, we contaminated using these type of outliers. So some outliers here, some outliers here, like that. 5 types of outliers. Okay. And how do we know if our tests are working good? So we define this word, the coverage. That coverage is the number of times the H0 is rejected. If H0 is true, we need our coverage to be near 0.5. I'm sorry, 0.05. Okay, 5%. So that means around 4 to 6% that we can consider that's working well. Okay, and if H0 is false, we need our coverage to be around 100%. Okay, that's basically the power. Now here we have some results. Okay, now this is not contaminated data. This is clean multivariate normal data. And in this case, actually the classical test is supposed to work very well, right? Because that's satisfying all the assumptions. Now let me take a look at this. So this column right here represents how many variables we have. Okay, how many measurements you have. N1, N2 represent what are the data, the sample sizes. Okay, I'm considering both balanced and unbalanced designs here, and sigma equal to 1, 2 represents covariances are the same or the different, right? Now, what does that be? Remember, we need bootstrap samples. Taking 1,000 bootstrap samples is no big deal, but it's still time consuming, right? We wanted to check if our test would work with a small amount of bootstrap samples. So that's why we changed that B to 250 and 1,000, and here 750,000. And turned out actually it does work very well with smallest bootstrap samples. Okay. Now, these numbers are supposed to be close to 0.05. Actually, they are, right? Except for the classical one. If you look at these numbers, those are very small. So that tells us the classical test in that case is too conservative. Okay. You might be wondering why I have only 1 point here, because in the classical test we don't use bootstraps, right? I have 2 lines because I'm using 2 bootstraps sizes here, but the classical doesn't need 2 bootstraps. Right, so that's the multivariate normal data. This is the clean mixture data. It's the same thing. Okay, all our tests are consistent around 0.05, but the classical test can be too conservative sometimes. Multivariate T data, same story here, and the log normal data here. Just take a look at the median. That will tell you about the type 1 error rate about this test. Since this is highly skewed, when the covariances are different, the mean measurements were different. Okay, so we were getting more of the power rather than the type 1 error rates. So that's why those numbers are close to 1. Anyway, that's about the type 1 error rates. How about the power? First of all, well, before I go into the power, this is the output for the, part of the output for the outlier simulation, okay? Now let me explain this table here. These are the different types of distributions, and these are the outlier types that I mentioned earlier, okay? Let's see. This gamma represents how many outliers are there. So basically 0.4 means 40% of outliers, and 1.1 means 10% of outliers. Okay, now let me start with the classical, okay? So what's happening here? So I have 2 groups, some outliers in one group, okay? Actually these 2 groups are the same except for that outlier, okay? So this test should recognize these outliers and maybe eliminate or ignore those outliers and test if these are the same. It should tell us that it's the same. So the number should be close to 0.05, but if you look at these numbers are close to 1. That means it's saying these two populations are different. Okay. If you go to the RMB, the test with the RMBN estimator in it, it is close to 0.5. That means it is recognizing these outliers and saying these groups are the same, even though we are having 40% of outliers in one group. Okay? So the test with the RMBN estimator is pretty strong. It could recognize up to 40% of outliers. But most of our tests failed with that many outliers. Okay? Now the PM represent this column right here. That represents how far away the sorry about that. There you go. So this PM represents how far away from the, how far the outliers are from the bulk of the data. But if you move this a little further, then the medians start to work very well. But again, with small percentage of outliers. Okay. So what I'm trying to say here is, if you think in your data set you have a very small amount of outliers, you go with the test with the median in it. Okay, because the test with the RMBN can be a little slow. So, but if you have no idea about your data, just go with the test with the RMBN estimator. Okay, that will give you pretty good results. Now here's the power simulation. Here's the setup. So to do the power simulation in our coding, we had to move the means far away a little bit. Okay, and depending on the number of parameters, these means will shift a little bit further away from each other. Okay. Otherwise, it can be hard to detect. Alright, now here are the power simulation results. So these numbers are supposed to be close to 1, right? So if you look at the first line, well actually I'm just using the balanced design here, okay? First line, all the numbers are close to 1, so we are good, right? And this delta represents the distance between the means, okay? Now, if you go down here, these numbers are not very close to 1, right? Why is that? Because I want to keep this 0.35 constant. If I move that a little bit further, all the numbers became 1, okay? I didn't want to show you a table with all ones in it because then it's pointless. We cannot compare those numbers, okay? But take my word for it, if you move the means a little bit further away, it will give you pretty good power, okay? Now that's the multivariate normal data. This is mixture data and multivariate T data all are acting the same. And here's the log normal data. Right. So that's the simulation. All right. Now you don't really have to trust the simulation results, but how about a real data example? Okay. So this example, actually this is a famous data set. It has 252 observations with 15 variables in it, but it didn't have a categorical variable. Remember, we are doing a 2-sample test. We need a categorical variable to divide this data set into 2 pieces. But we came up with a variable. We came up with 2 age groups. Okay. Now we want to see if these 2 groups are the same or if they are different. Right. So let's take a look. These are the results. Now, I ran the test with the RM median and the code-wise median in it. It gives us consistent results and it failed to reach a pledge node. What does that mean? That means it is saying these 2 groups are about the same. But the classical test though, it says otherwise. Okay. Now what we're going to do? Are we going to trust this result or this result? Okay. How can we do that? So once I have these results, I take a look at the data. So right here. So this is a DD plot. I got 2 DD plots for those 2 groups. If you're working with multivariate data, it's a very good way to visualize your data. It gives you a lot of things. One thing is it will give you a sense of outliers. Okay. So now see those points sticking out from the bulk of the data? Those can be considered as outliers. Okay. Actually, DD plots tells you about the distribution and a lot of things, but it's not important here. Anyway, I went into the data set and I removed those outliers by hand. Okay? And then let's see what's happening now. Now the test, well, of course these numbers would be different because now the data set is different, right? No outliers. Still, our tests are saying those 2 groups are the same. Okay? And the classical test, well, now it agrees with our decision. Okay, say the jump of the p-value 0.001 to 0.09, so that's a pretty good jump. So classical test couldn't handle those outliers, but our test could handle those outliers. All right. Now that is all about the 2-sample case. Right now, I think we are ready to move to the 1B MANOVA test. So these are the alternative tests for the one classical MANOVA test. Right now here, this is actually a theorem that we came up with. If you notice, it is not using the same covariance structure among the groups. Okay? Remember the classical MANOVA test? It uses it assumes the same covariance structure among the groups, but this theorem doesn't assume that. Using that theorem, we came up with a large sample test to do the 1B MANOVA test. So, using all this large sample theory, which I'm going to skip right now, you can come up with a test statistic. It's very similar to the Hoteling's T-square test proof. Came up with a T-node, and that's a chi-square distribution. Now, if you change that, well, again, I want to show you these are not using the same covariance structures, different covariances. And eventually we'll come to a F distribution. Okay? And I'll be showing the results. This is actually true. Okay? It works very well. It outperformed the 1B MANOVA test sometimes. Okay? Alright. Now that's that's one of the tests. That's the large sample test. Of course, it's not going to be robust to outliers. Okay? It is addressing only one but major assumptions. Okay, let's see. Now that's one test. We didn't stop there. Here are some other tests. All right. Now, if we use this model, what are the z, x, x and b? Well, I don't think I need those. So I'm trying to explain some stuff here, but why don't I show you those? Okay. All right. So Yij, if I look here, these are m measurements of, let's say something like that. These are m measurements of the jth person in the ith group. All right. So what we have done, we stack those vectors up in the z. All right. And then this x is just the indicator matrix. Okay. So the first column is just ones, and the second column is just an indicator for the first group. The third column is indicator for the second group, and likewise. All right. Once you have all that, and if you set your b to be like this, and instead of testing our hypothesis, the usual hypothesis mu1 up to mu p, we can test something like that. Okay. What is that actually? Okay. So my L is 0, 0, 0, 0, and 1. Something like that. Okay. So this 0 is actually a bold-faced 0 as a vector, and then you have the identity matrix. And if you multiply that with that b, what's happening? If you multiply this L with that b, this space will cancel out, right? And all you're going to have is mu1 minus mu p transpose equal to 0, and rest of equal to 0. What does that mean? That means mu1 equal to mu p, mu2 equal to mu p. Basically the same, mu1 up to mu p are the same. Alright? So, using that, we can come to a new test. Again, so I'm trying to explain here why we are going away from our last sample test to a different test. Again, that is because sometimes these, even though it doesn't use as the assumption, estimating those covariances for those groups sometimes impossible or sometimes can be very high. So that's why we are moving. Oops. That's why we are moving from that large sample test to a different test. All right. So now this can be a very good alternative in that case. Okay. Now, how to do those tests, right? Remember in the two sample case, all we were doing is we were setting our Wi to be the difference between the code-wise median or the means. But here we are bootstrapping LB hat, LB hats. Okay, what are those? Just like I explained before. Okay. Now these are consistent. This is a consistent estimator for mu1. And if you want a robust test, you can change those to a code-wise median or the trim mean, or you can use the RMV as location estimator. Okay. So you do all that, you bootstrap your Ws, and then you make the prediction region and see if the 0 is inside the prediction region. Okay. So you basically do the test the same way, but it's slightly complicated than the previous test. All right. Okay. Well, I could show you a bunch of tables, but I can show you something much better. Okay. Now this is, what is this? So this is for the multivariate normal data with I have 5 measurements. Okay, and it is a balanced design. Okay. Now the classical test should work better here, right? Actually it does. You see this line right here? So that's our classical test. It's working very well because that's the perfect model for the classical test. Okay? The covariances are the same, it's coming from multivariate normal data, and it is a balanced design. Okay? What else you could ask for? So once you have all that, the classical test works pretty well. Actually our test with what? The mean? Yes. So the test with the bootstrap test with the mean just follows that curve. Right? Now, well, I actually forgot to explain what this curve is, right? So this is actually the coverage, and this delta 1 represents how far the means are from each other. Okay. Now, when delta is 0, means all the means were the same. okay? And they were all 0. And every test is considering here around 0.05, which is basically the type 1 error rate, right? Now, when you're moving the means a little further from each other, the curve should get closer to 1, right? So that's what's happening, right? But if you notice, we don't have our large sample MANOVA type test over there, but in the next graph I do have that, okay? Any questions so far? All right, so let's take a look at the other one. So all I did was, I changed this to unbalanced design. Let's see what's happening. Look at that. Now this is the classical test. Only change was, I changed that to unbalanced design, then classical started to do bad. Okay? Now this, I included my MANOVA type test here. Okay? Which is hard to tell. Well, the blue line right here. That's our MANOVA type, the large sample test, and all the other tests are bootstrap tests. Okay? All the tests are working pretty well, except for the classical one. Maybe this is not very good, but at least more than one of our tests are working well. All right. Now that's the multivariate normal data. And how about multivariate T data? That's unbalanced design again. Again, the classical is not doing very well. Okay. And those graphs makes me happy every time I look at them. All right. Now, how about a real data example? Okay. Now, this data set consists of 630 observations and 24 variables. I'm not using all 24 variables, but I'm just using these 5 variables. And this is a very well unbalanced design. So the group 2 has little more than half of the sample size of the group 3. Okay? And let's see how this data looks like. All right. Before I do my analysis, I take a look at the data, and these are the dB plots for those 3 groups, and it has some outliers. Okay, and also the side-by-side box plots shows me these populations are about the same, but they are highly skewed, right? And it has all those outliers as well, right? Now let's take a look at the results. So these are the new test results. I don't have our last sample testing here, but this is the test with the median in it. And it failed to reject H node and saying these groups are similar in terms of those 5 variables. But the classical one with MANOVA test says these are different, okay, which is not surprising. The classical test doesn't do very well with the unbalanced design and also with those different levels of skewness. Okay, so I guess that's the end. And these are some references I've used. And the first part of the talk is actually based on this paper that Lasante and I submitted recently. Just the bootstraps and lots of the 2 sample T-square test. Right. So thank you so much for coming. Thank you.
Do you have any question for the speaker?
All right, because I can ask the question.
Sure.
I think a few slides ago you had one in the type 1 error slide.
Okay.
Those were very high, and you made a comment that they're high is okay because it's like a power. So if you can explain
Yeah.
that, I would really.
This one. So in the simulation, actually the means were shifted here. Only the medians were 0. So that's why it's giving us a sense of power rather than the type 1 error rate. So it's just about in the simulation. Is that the slide? So classical isn't doing anything bad over there because just means were shifted.
So it's taking the other mean as a H0.
Right. Right.
Any other questions?